So yeah, thanks for letting me present this. Yeah, so those who haven't already talked to, I'm Philip. I am doing a postdoc in Padova, where I work with Luca these days, mostly on CP validating actions. But during my PhD, I worked a lot on kinetic misalignment, which is what I'll talk about now. Yeah, so also thanks to the organizers for organizing this very nice workshop. It's my last day today, and I very much enjoyed it. Okay, so I'll both present some of the stuff I worked on and also try to just explain to you what this what the concept of kinetic misalignment is. Therefore, I subtitled my talk what it is, what does it do, and how do you get it. So let me start with a bit of background. So the usual way we think of axion, both QCD axions and ELVs as being produced as dark matter is through misalignment. And the way you get misalignment, which I here call standard misalignment, is so you have this periodic potential, but when you write the equation of motion in expanding space-time, you both get the term from the mass when you expand around the minimum, and also this friction term from the expansion of the universe. And this means you have two limits. One limit in which the friction term dominates. In this limit, the field is frozen and the energy density doesn't evolve. And then in the other limit, where the mass dominates, the field is oscillating and behaves like dark matter. So the way you make standard misalignment work is that you assume you start with some non-zero initial angle, no initial velocity, and then initially you're frozen in place by the friction term until eventually the mass term dominates and you start oscillating. And then an oscillating scalar field behaves like dark matter. So from this, you get a dark matter relic. So this is all standard. And what I want to point out here is that the relic you get scales with the decay constant. So if we look in the ALP parameter space, as you go to larger decay constants, then this tends to overproduce unless you tune your initial angle towards the minimum. And as you go to lower decay constants, where the ALPs tend to couple more strongly, then you underproduce the dark matter. So in this plot, I just assume the case we see like coupling. But this is generic. So it's interesting to ask whether there are more production mechanisms where you can also account for axion, both QCD axion and ALP dark matter in the low FA regime. That's really the central question today, whether we can produce ALP dark matter at low FA. There have been some different proposals on how to do this, both trying to tune to the peak of the cosine. Some people here who worked on trapped misalignment. But the one we'll be talking about today is kinetic misalignment. So kinetic misalignment, it's a new framework for producing axion dark matter at low FA. It mostly associated with Ko et al. Because they produced a number of papers on this topic, but really it was proposed independently by both Ko et al. And Chang and Choi in 2019. So she also gets some credit. And the key idea behind this is really that you drop this assumption that I mentioned before, is that the field starts with lower initial velocity, and you instead assume that it starts with a large initial velocity. And by large, I mean so large that instead of starting frozen in place, you're rolling over many barriers. And of course, Hubble friction will continuously drain away this kinetic energy, but you will continue rolling, passing barriers until such time that Hubble friction drains enough kinetic energy that eventually you become trapped in a minimum. But the important point here is that if you have enough kinetic energy, you can continue rolling until long after the time where you would have started oscillations from standard misalignment. So in this way, you can delay oscillations. That means less redshift, as therefore more dark matter relative to standard misalignment. And therefore, you can account for dark matter at lower decay constants. So that's the overarching idea of kinetic misalignment. Let me talk a bit about what it does. So of course, it's made for dark matter production. One way to understand this is by thinking of the conserved quantities. So first, let me talk about the rolling regime. Usually we think of the action as the angular degree of freedom in a complex scalar field. So rolling really means rotating, spinning in around the minimum here. And in this regime, we have a conserved quantity corresponding to the Noether current of the shift symmetry, which is this charge here. It's here labeled NPQ. And really, it's the analog of the angular momentum of this field. Eventually, the shift symmetry is broken when the mass becomes significant, and this is no longer conserved. And instead, in the WKB limit, you have another conserved quantity, which is the axion particle number density. And it turns out that these are not two different variables. They're really two aspects of the same variable, and they're related just up to a factor 2. And this was pointed out by Ko et al. And we also showed exactly that it's exactly 2 in our work here with Jem, that was here last week, Bosoko Sato, and Geraldine Savant.
Without sources of breaking statement,
so you can, well, with the mass you the mass you oscillate in. So this is true both in the regime where you're oscillating and where you're spinning. You can relate the two quantities there by looking at like axion variable. So I can show you afterwards, see if I remember it exactly. But you can relate it because they're really two expressions of the same, more general conserved quantity. So therefore, if you can generate an angular momentum of this field, this conserved quantity here, this corresponds directly to having produced a number density today. Yeah.
There is something in the equation.
Here. Yeah, it's theta dot. It's theta dot. Yeah. So this here is the number density, which you can measure at any time before you start oscillating, where it's conserved, and then it will be translated to number density today. Then you get a relic. And this looks very much like the relic you got from standard misalignment. But the point here is that the time you have to start redshifting from isn't set by competing with Hubble, but just with theta dot competing with MA. So by choosing your initial velocity, you can choose when this year starts redshifting from. Yeah, so you can get this way. You can get a much larger relic density.
Is that intuitive way? And the number density is exactly twice.
Intuitive way. So
it seems like it's difficult to very different.
Yeah. So I tried praying. Yeah, I'm not sure. Sorry.
I guess at the time of oscillation.
You can calculate this long before. This is constant before you start oscillating. MPQ divided by S. It's conserved. Yeah. So in expanding space-time, it scales like h to the -3. So NPQ over entropy is constant. So before you start oscillating, this here, NPQ over S is constant. And after you start oscillating, NA over S is constant. So the conserved quantity is either of these, depending on which regime you're in, but you can calculate either, and they're related. Okay, yeah, okay, yeah, true. We really should have divided out by the entropy density. True, yeah. Okay, that's true. Really, I should have divided out by the entropy density here at the relevant times. That's a true statement. Yeah, that's a good point. You can take this to be valid, like at the transition. Yeah.
Essentially, you can understand it as a coherent state. So then there is one. If it means, then of course the axion number becomes very positive because the interaction is important. So axions are no longer shared. But still, I mean, this relation, actually, you can define axion number in optional case as something proportional to charge. They are related.
Yeah, so I haven't thought of this, but it's probably true. Yeah. Yeah, the relevant conserved quantity in the limit is the PQ charge. Yeah.
But if it's spinning, then okay, I mean spinning field, then you have to, okay, you can still understand it as bunch of boxes.
Yeah. Yeah, it's hard to understand as like unshelled particles. Yeah. You have to wait for the oscillations to be in the WKB limit before you can understand them as unshelled. Yeah. Yeah. If it's conserved, then it just dilutes with the redshift. Yeah. Yeah. So just expands. It is just diluted by the expansion. Yeah.
Because I mean, spinning
yeah.
produce fermions, for example, or photons. But that's unimportant. That we can ignore.
You mean from resonance or something? Or
spinning that will produce particles. Independent field. If you write, for example, direct fermions.
Yeah.
Background.
Yeah. But maybe we should discuss this after the talk, because otherwise I get really far behind on what I want to say. Yeah. We just keep the conserved charge in the field. Yeah. It's an additional friction which we're not accounting for. Yeah. Okay. So by giving enough kinetic energy, you can produce more dark matter. And in fact, you're postponing oscillations. Of course, you can keep doing this indefinitely. Another thing kinetic misalignment can do is that it can mess with BBN. So to see this, just have to think at the conserved charge. If it's conserved, it has to just dilute with the expansion, (-3). That means the energy density in the kinetic energy goes (-6). So that if you have onset of oscillations here, then before that, the energy density will compete more and more with radiation. And of course, if it's competing too much during PBN, then you are ruled out. So calculate a constraint from this just by feeding this energy density to BBN code, which gives you a lower bound on how late you can delay oscillations to. So that's one bound you get. Another interesting effect that happens as you begin to postpone more and more is axion fragmentation. So axion fragmentation is really, this was studied by also some postdocs at DESI when I arrived there. And it's really a phenomena in the fluctuations. So to see this, you just expand the angular mode in higher modes. And what you see is that the equation of motion is a Hills equation, which tells you that these modes can, under the right condition, experience exponential growth. So If this occurs, then the fluctuations can grow and back react on the homogeneous mode. So this means that the homogeneous mode is totally disrupted, and if in effect all the energy is dumped into fluctuations. This is what we mean by fragmentation. And it's dumped into mildly relativistic axions. Because they're only mildly relativistic, this doesn't really have a major impact on the dark matter relic. It's about it's more or less unchanged. But it can, since we don't produce absolutely cold axions, it can have consequences for formation of structure. You can get some mini clusters. And we also wanted to see if you get a gravitational wave signal from this. Unfortunately, the gravitational wave signal, which we calculated, is way too weak to be observable. But my collaborator Jim did find some signatures in mini clusters that I will get back to later. We also tried to classify how the efficiency of fragmentation, and we found that it is essentially controlled by the hierarchy of the mass to Hubble at the time where oscillations start. This makes intuitive sense because what prevents you from probing the anharmonicities in the cosine potential normally is that Hubble very quickly dampens you into the WKB regime. But if Hubble is weak, then you can probe the regime where you can produce resonances much longer. So if the mass is smaller than Hubble, when you run out of kinetic energy, you're frozen in and you just have to wait for standard misalignment. If it's a little bigger than Hubble, then you have kinetic misalignment in the form that was envisioned by Koh et al. If you try to push it further, then the mass becomes so large, you really probe the anharmonicities and have fragmentation while oscillating in the cosine potential. And if you push it even further, then you can have fragmentation even before the field stops. And we can map this back onto the MA-FA plane. So T star is the time where the rolling stops. You run out of kinetic energy. Yeah, I would say trapping, but that's not exactly true if you end up fragmenting. In practice, fragmentation becomes more efficient as the field slows down, and as such happens right before it would have trapped. So you can take it to, you can understand it as the trapping temperature, but the more precise statement will be the time where you stop rolling. That's T star. Yeah, I didn't, thanks for asking, that was not entirely clear. Okay, but with this, you can then, given enough kinetic energy, you can extend upwards from the standard misalignment regime. And you have a regime in which you have kinetic misalignment with a homogeneous, just regular oscillations. You have one where you have fragmentation after trapping and one with fragmentation before trapping. And give it enough kinetic energy, you can account for dark matter in these regimes with kinetic misalignment. Yeah. So this is, of course, very nice. But at this point, the elephant in the room should really be, how do you get this kinetic energy? I mean, it's all very nice. We can saturate this with a lot of kinetic energy, but if we can't account for how that comes about, then we haven't come very far. So the next part of my talk is how do we get this? This I also worked on in my PhD. And the way that Koh et al. Proposed that we can do this is by simply reusing Affleck-Dine baryogenesis. Because what Affleck-Dine baryogenesis does is that it spins up a complex scalar field, giving you the conserved charge in the complex scalar field. And then in Affleck-Dine baryogenesis, you transfer that conserved charge to the baryon number. That's the principle behind kinetic baryogenesis, Affleck-Dine baryogenesis. So all we have to do to repurpose this for kinetic misalignment is simply keep the conserved charge in the field such that it ends up as an Axion number density once the field starts oscillating, instead of being transferred to the baryons. In fact, Koh et al. They also used this to transfer part of it to baryons to get axiogenesis. So, but it's really because it's a repurposed baryogenesis model. So for those of you not very familiar with how affect-ion baryogenesis works, let me just go through how this works. What you do is that you introduce higher dimensional operators, Pn, over some large scale, where P is the full complex scalar field. And then this gives you an angular gradient that you only feel at very large field values. So because of this, if you start rolling from some large radial wave, then you will feel the angular gradient and start rotating. But you will very quickly redshift out of reach of this potential so that you continue rotating once you turn back. So with this setup, like in this event, which we refer to as the kick, you generate an initial angular velocity and generate this conserved charge, which can then either be used to generate baryons or keep it for an axion number density. So, of course, you also need this large radial wave. And the way that also Dine et al. Did this is that in addition to generating a low, like a small radial mass through soft SUSY breaking, you have to appeal to SUSY. Then you also, in addition to generating a small radial mass, much smaller than FA, and including these higher dimensional terms, you also couple it to the energy density through a Planck suppressed operator, such that you get a finite, like a finite density correction, a finite, like a mass contribution from this coupling that's proportional to Hubble. And this can appear either with a positive or minus, positive or negative sign. And if you have this mass correction appearing with a negative sign, you can make the origin unstable at early times, driving you to a large wave where you can stabilize against the higher dimensional terms. So at early times, you're really sitting in the minimum set between this negative contribution and the higher dimensional operators. And then the kick happens when you roll out of this early minimum towards the zero temperature potential. And then you initiate the rotation there.
So here you are
We're considering either QCD axion or L.
for QCD axion, we have to be extremely careful not to break the J explicitly. I mean, that may completely ruin it.
Yeah. No, this is true. You have to be careful that you don't ruin the axion quality. But yeah, so what you have to do is only introduce higher dimensional operators with an n large enough that you don't break the quality. You don't move theta too far. Yeah, so to not give theta a wave larger than 10 to the minus 10. So in this form, A here is a dimensionful constant related to the axion mass. So it's in this here, I think it's something like n has to be larger than 8 or something to not ruin the quality, depending on where you are in the regime.
In fact, nevertheless, we are saying that it's sufficient because you see, intuitively, I really understand that it's something that would give it a real kick.
Yeah.
It means that you are
But yeah. But the point is that you only feel this significantly at very large field values. So as you redshift the radial mode towards you start much larger than FA, and you redshift down to FA, and then you don't feel it as strongly anymore. Yeah, because you probe at a large field value. That's the trick. That's a trick. This can work for QCD axion, because by starting a large field value and then falling down to a smaller one, you essentially get like an PQ breaking that turns off as you go to smaller field values.
So there's an alternative way to not touch the quality. If you would do this thing through the QCD scale, QCD scale during inflation can be very high because the QCD scale is a parameter, is a field.
Yeah.
Depends on any field that couples to SF2 or sorry. When it changes, the vertical changes, it's coupling to QCD. So there's a pretty natural parameter range in which during inflation, QCD scale can be very high. And that would give a kick to the Axion, which of course will not affect the quality problem, but it's all coming from QCD. So it's the same potential.
So you mean not just a large radial wave, but also rotation?
Well, it depends on the so it's like a wing, but you have a wing load.
Right. So I'm afraid I'm running low on time. Yeah. Yeah. According to my clock, I have just 4 minutes left. Yes. Here. Yeah. All other n. You have to, okay, it's not. It changes if you include lower ones. Yeah, so a strong assumption you have to make is you don't include smaller powers. So are the PQ preserving ones? Yeah, these ones. So they would affect your initial wave. Yeah. I guess they would interfere with the kick in that they give you a smaller radial wave, which makes the effect from these high dimension operators much smaller. So you have to get a significant kick, you have to not have those.
Can I check the initial value of theta? The initial value of theta you get there.
Initial value of theta dot. Yeah, because it's not so far from. Yeah, it's not. It's comparable to Hubble, because you get a roughly slightly elliptical orbit, which means that the angular velocity is comparable to m phi. Yeah, and which is at this time they transition at the time of Hubble, so they are of a similar order. Okay, I have to speed up. One thing you have to do really carefully when you do this is you have to care about the radial dynamics, because you don't just get a rotation, you also get radial oscillations. You're not oscillating around the origin because you're competing with the centrifugal term. So this is really a Kepler problem. You have an elliptic orbit oscillating about some effective minimum set by the angular velocity. But still, nonetheless, you have a scalar field with an oscillating scalar field, which behaves as dark matter. So if you really want to insist that this should be the initial condition for kinetic misalignment, then you have to dampen away these radial oscillations. So you have to have a coupling responsible for damping out, providing a friction to these radial oscillations so you can dampen them out. And this is something we felt needed more careful treatment. So in my thesis, I considered explicit couplings. Take, for instance, a KSVC like Yukawa coupling. And then we included all the thermal damping rates and the thermal effects from the thermal contributions to the potential. And then I put that together in a numerical. I then numerically integrated the Boltzmann equations to really account for some of the unexpected effects you can have when the thermal damping rate depends on the plasma, which is heated by dumping energy into it. This can lead to otherwise some unexpected effects, but we numerically integrate it all so we can have so account for these nonlinear, like these unexpected contributions. And by integrating all this up, we can map out the part of the MAFA plane which this mechanism can provide the initial conditions for kinetic misalignment for. So it's a fraction of the one we showed before. For these ones, we can show that we really can provide the mechanism to give the initial conditions for. So we still can get a few orders of magnitude extra for the QCD action, and we can also provide ALPS. We can also generate ALP dark matter in a parameter space and reach about a lot of haloscopes. And interestingly, also, if IAXO or ALPS2 found something, this motivates that they could also be dark matter. Yeah. One thing we also really wanted to make sure that was under control was the parameter values you need to put in these UV potentials. So, because this was not really reported on in the work by Ko et al. So we also map out the parameter values you need in order to get this to work consistently. So for instance, here, it's just an example of some of the parameters. This is the Yukawa coupling I mentioned earlier. So we map out, it has to be not so large that the thermal effects ruins your kick, but not so small that you can use it to dampen with. And we map all the parameter ranges you need. So just to sum up, I figured people are probably lost in their assumptions. So let me just paint the assumptions you need for this. So to get this to work, you first assume SUSY. You then generate a small mass from soft SUSY breaking. You introduce these high dimensional terms. If you want it to be QCD action, you need the N to be large enough not to mess with the quality problem. Then you assume that it's coupled in a way that makes the origin unstable. So you push to a large VEV. And then you need some coupling responsible for dampening the radial oscillations. Could be a KSVC like Yukawa coupling, could also be a Higgs bottle. And these have to be small enough to not have thermal effects ruin your day, but also large enough that you can still dampen with them. I didn't mention it so much, but there's also some slight assumptions on your inflation model. We just have to have a T reheat larger than the temperature where the kick happens, and we also found out that you can't just allow any spectrum of curvature fluctuations from inflation. You need the spectrum of curvature fluctuations from inflation to be at least a few orders of magnitude the value suggested by the value measured at Planck. But this is totally unconstrained, so this is perfectly in line with observations. It's just a slight, just something your inflation model has to satisfy. Yeah, I wanted to also just point out some signatures. I already mentioned you can get some mini clusters. This my collaborator Cem studied, and in this region highlighted here, you could have potentially some photometric lensing signatures. This is directly from fragmentation. From the implementation, what you could get, it's a little hard to see, but what you could get is that you can get an enhancement of the primordial spectrum of gravitational waves. Because if you have a period in which this kinetic energy dominates the universe, you can create a peak in the primordial spectrum of gravitational waves. So you could potentially have some regions where you could get a observable gravitational wave signal in future observatories. But it should be stressed here that this depends sharply on the amplitude of the primordial spectrum, which depends sharply on the inflation scale. Yeah. So these are the frequency and the amplitude are in line with these experiments. Yeah.
It's like so okay, so very low frequency.
Yeah.
Around the 1 F.
Yeah, it's fairly different. Yeah. It's not a good day for LIGO. Yeah, but this only really works with the very highest allowed inflation scales, because it goes with the inflation scale to the 4th. So if the inflation scale is any smaller than the maximum allowed, then the signal goes away immediately. So if we have to be lucky and have near the maximally allowed inflation scale, and then we could in future observatories here. So it's not the most promising, but it's a signal that could be possible if we are really lucky. At any rate, it couldn't rule out the model, but it could provide a confirmation. Yeah. Okay. I think that's it. Summary: if you had Axion Kinetic Misalignment, you could motivate Axion and both QCD Axion and ALP dark matter at lower FA. You could get ALP dark matter in the reach of haloscopes and future experiments. Much of the parameter space will feature fragmentation. The gravitational wave signal, which we calculated, it's too weak to observe, but there may have more luck searching parametric lensing from mini clusters, and that you can make model implementations, and we mapped out consistently how this can be done with this F-like dying-like setup. Yeah. Cool. I think that's my time.
So I think another way to get light level mode could be to approximate the variance and make the number. Something like that. I think there's a way that.
Then you could naturally get a small M5.
Small M5, yes.
Yeah.
But then that's not sufficient, of course.
You still need these high dimensional operators, but those are not so bad. Those are not such a strong assumption.
Yeah, but it's really, what do you really need? It's not just
you need the light radial mode. You need to make the origin unstable. You need the high dimensional operators.
The origin is stable.
So so also F-like did this. You introduce a coupling. I think it's a Planck suppressed operator to the density, to the dominant part of the energy density, which then gives you a mass contribution on the order of Hubble with some order 1 factor, which may be negative. Yeah. Yeah. So there are some papers also on how you get these operators, but they like you can the people who claim you can get them both depending just on the inflation scale, but also with Hubble during like radiation domination.
Which area do you need parametrically? How light is it?
It depends on where in parameter space. So if you want to stay at the relatively high Axion masses, you need less of a hierarchy. Then you only need a few over like hierarchy of a few. But if you want to go to lower action masses, they can become really, really large. You need very light axial radial masses. It scales with the axial mass, so you get respectable power. Yeah.
Yeah, I was gonna ask you about, I would like to ask question. Is, for instance, in the QCD action, for instance, sure you have to calculate the action of the photons, right? Data effective. So that's going to produce, if theta dot is very large, we're going to produce a lot of photons at the expense of the kinetic energy of the action. And it's been studied.
So
it's potentially even much larger effect.
So friction from photon production with a large theta dot. I have to think about this. I don't have an offhand answer.
But what's the friction more? I mean, the larger the theta dot, the theory is very.
I think this effect has not been considered by Cole.
No.
Yeah, that's what I'm asking.
It's a product.
I mean, I for sure don't have a good answer.
I think that, I mean, the larger theta dot, the larger the effect will be.
Yeah.
So, but actually, we have to believe that there are combinations and variations. Yeah, and they will say. Another thing we also study is that you could also create a lot of Axion programs. I think they use that in order to get additional. So I think if they didn't study specifically for photons, I guess it's because they're using the same mechanism.
Sorry, which paper was this?
Is a radiation too.
I guess they're using to account that if you already is zero, then you get that they come into photons due to the mix, right? In the but when you turn on to CD, already this is oscillating, right? So this is rolling for the CD. The Axion is going with the volume of time for lambda QCD. Then lambda QCD starts, right? And then at some point it becomes flat. So there's a sort of period in which simultaneously you have significant effects of QCD and large rolling. So it could happen in that region. I'm just saying that it wouldn't apply.
I mean, Axion covers the photon from the beginning.
Well, depending if E over M is zero, doesn't, right? If E over M, the anomaly is the electromagnetic anomaly.
So assuming there's an anomaly.
But that could be zero, exactly. That's not independent.
Sorry, also radiation to two. You don't get rid of it.
So
Thermal mass, plasma mass.
Normally, you have kinetic energy is high. The Axion,
it depends on how high it is.
of course, that's
But in the beginning, possibly it's rotational, right?
I mean, if you see it right away like that, yeah, I don't see it. This is something that's studied. Depending how much kinetic energy. So the question is. Question is.
Accurate.
When there, the decaying photon of the particle, because of the stuff in the assuming, interferes with this effect and provides much stronger friction. That's the question.
It's a good point. There's something we should check.
Priori, okay, not clear. Perhaps there is a regional parameter.
That was another question years ago. Oh,
No.
Marco.
So I know that people ask this,
So which problem? So that depends a bit. So in the setup I presented here, you don't have that because the field is heavy during inflation. It's heavy during inflation. Actually, both from the higher dimensional operators. When you're sitting in this early minimum, the fields are heavy, and the fluctuations go away. Which, sorry? It's very, very homogeneous. No, you. Why would you, sorry, interpolate? Why would you interpolate? It's homogeneous. Sorry. Mm-hmm. Yeah. So if you have fluctuations in the field initially, they can grow during the rotation. It's a significant problem for another family of models that Ko et al. Studied, which you also studied, where you set the radial VEF just with having the field light and then have the setup fluctuations. But the problem with this is that that you have, since the field is light during inflation, then the small fluctuations in the kick from that will land you in different minima, and you will have domain walls. And this is worse than the standard problem because you get domain walls without strings. So they're much harder to get rid of. Yeah, but this is not a problem for the nearly quadratic model because they're really heavy during inflation. So these fluctuations go away. You don't get the domain walls when they're heavy during inflation, only when they're light and they pick up fluctuations. Yeah, but in that case, it's a severe problem, I agree. Which is why I didn't talk about that model here, because it has a list of problems. Yeah.
Okay. Any other question?
Well, I had a small issue with the role of supersymmetry.
Yes.
Oh, so the role here, what? So we need a justification for getting a much M5 much smaller than FA. If you did this just with a straight quartic potential or something, then you would have to tune a lot in order to get this much smaller. So the role of supersymmetry here is there's a justification for getting a smaller to justify this hierarchy. But I mean, you don't. It's not crucial. It's in this setup.
Maybe you are also talking about the configuration.
Yeah, you care about the radial mass. The radial mass will be much smaller than FA. But as Luca mentioned, there are maybe ways you can do this without appealing to like a mass generator substance break. FA. The K constant, yeah. 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 If the radial mass was as large as in the standard case of order FA, then this would suppress the radial VEF you could achieve, and you wouldn't able to probe these high dimensional operators without ruining the late effects. You wouldn't be able to have a hierarchy enough.
I think it was going to so that the mass of the moduli is coupled, even in minimum case. So the moduli, they get mass of H square.
Okay, yeah.
Because of supersymmetry, because the expanding universe supersymmetry is from the scalar function to always generate mass of H square, and not the whole mass. So previously people, there were papers that were saying that, for example, if mass is small, supersymmetry, but no, because every universe breaks.
Yeah.
So the mass is always H square.
Yeah.
But yeah. So
I think Affleck and Dine, they also had these terms in their model, yeah.
well, before they were thinking that the mass was around TV or something like that. Yeah, then later people started writing papers about like that incident.
Who is at least like Dine Randall Thomas in
Well,
yeah, okay, yeah,
I had some of that direction.
yeah. Yeah, so I don't remember what kind of potential they had in the 85 paper, but in the Randall Thomas, yeah,
They also had some kind of specific mechanism for biogen. No, I didn't enter there, but
yeah,
that even in supersymmetry, you should not assume that the modular masses are less than the couple. Because they can never be less than the couple because every universe breaks supersymmetry.
Yeah. That's what that's what we need, right? Yeah, it's nice. Yeah, it's very generic with supersymmetry. Yeah, that's very good.
Okay, here's lunchtime, so we thank
Mhm, mhm.